Hi everyone. In the last two lectures, we have described about semi-inner product spaces as well as inner product spaces. In the today's lecture, we are going to discuss these 3 points. How to get an inner product from a given semi-inner product, that is the first question. And the second question is that given a norm on a vector space X, does there exist an inner product which induces the given norm? This is the second question. And we are going to discuss about Hilbert spaces also. Let us come to the question 1. So suppose X with this two variable function is a semi-inner product space. That means there may exist vectors such that the semi-inner product of that vector with itself is 0, but the vector is non-zero. So let us collect all such vectors. Let n to n be set of all x in X such that semi-inner product of X with itself is 0. Now we can show that this is a vector space as well as it's a closed subspace of X. Let us look at that part. Let us take X and Y from N. We want to show that X plus Y is in N. That means we want to show that semi-inner product of X plus Y with itself is 0 whenever X and Y are coming from N. Okay, so this is we want to show. So let us consider this part. X plus Y semi-inner product with itself. This is semi-inner product of X with itself plus semi-inner product of X with Y plus semi-inner product of Y with X plus semi-inner product of Y with Y. Now we know that semi-inner product of X with itself is 0. Similarly, semi-inner product of Y with itself is 0. So this is 0 and this is also 0. So we will remain with semi-inner product of X with Y, and the second one we can write as semi-inner product of X with Y bar when the field is complex. Otherwise we don't need to write this part. So this is 2 times real part of semi-inner product of X with Y. Now this is less than or equal to 2 times modulus of semi-inner product of X with Y. Now by the Cauchy-Schwarz inequality for semi-inner product spaces, this is again less than or equal to 2 times semi-inner product of X with itself and taking the square root multiplied by semi-inner product of Y with itself and square root. We know that X is in N and Y is in N, so the right hand side becomes 0. So this says that from this we can conclude that X plus Y is in script N. So similarly we can show that, so with this simple reasoning we can show that, so easy to check, and alpha is a element from field. This is alpha X is in N. This says that this N, whatever we have defined, is a vector subspace of X. Now we want to show that N is closed. Next claim is that N is closed. But this can be easily proved by using the fact that the semi-inner product is continuous with respect to two variables. that again follows from the Cauchy-Square inequality. So this is Cauchy-Square Bunyakovsky inequality. Okay, once this is a closed subspace, we can actually look at the quotient space. Let us take x tilde to be the quotient space of x with n. Now every element here is of the form x plus n, where x is coming from x. So if you take two elements from x tilde, let us take x plus n and y plus n. We want to define an inner product on this. So this is by definition semi-inner product of x with y. If you take y equal to x, and if you assume that x plus n, x plus n is 0, then on the right hand side, semi-inner product of x with x is 0, that means x is in n. So once x is in n, x plus n is nothing but n. That means n is the 0 element in the quotient space. Hence this satisfies the positive definite property. So we can conclude that this is an inner product on the quotient space. In fact, we can show the other examples very easily. So easily it can be verified that is an inner product on x tilde. Let us see one or two simple examples. The first one, let us recall from the earlier examples. Let us take x to be R2 and the field is R. Take x equal to x1 comma y1 and y as, we can take x to be x1 comma x2 and y as y1 comma y2. We have defined that semi-inner product of x with y as x1 y1. We have shown that this is a semi-inner product, and we can easily show that this is not an inner product. Now in this case, if you look at script n, that is set of all x1 x2 coming from n, such that x1 x2 semi-inner product with itself is 0. So this is nothing but set of all x1 comma x2 in n. This is x1 square is 0, so that is nothing but x1 is 0. So this is nothing but 0 comma x2 such that x1 is 0. Sorry, this is x2 is coming from R. Here this is x. So this is nothing but y-axis. So if you look at the picture in R2, so this is 0 0, this is our n. If you take x as x1 comma x2, if I take a point here x1 comma x2, so this point will be x1 and this point will be x2. Now x plus n is nothing but the line passing through x1, and now this is 0 if and only if x1 is 0. That means whenever it coincides with y-axis, then this becomes a 0 element, and the inner product of any two such lines is given by the earlier equation like this. So that means if I take x as x1 x2, y as y1 y2, then inner product of x plus n with y plus n, this is nothing but x1 multiplied by y1. This is the inner product on the quotient space. Quotient space is nothing but all the lines which are parallel to y axis, that is the quotient space. It consists of equivalence classes. Okay, this is the first example. Let us look at one more important example that we will be using again and again throughout the course. Let us take AB in R with A less than B. Define script L2 of AB as set of all functions from closed interval AB to C such that f is measurable and integration from A to B mod f square d lambda is finite. Here lambda is the Lebesgue measure. On AB, or we can say on the Borel subsets of closed interval AB. Okay, now here we define the semi-inner product like this for any f and g coming from L to AB. We can say that this is integral A to B f g bar d lambda. So if you look at script n, set of all f in this space such that the semi-inner product of f with itself is 0, but this is nothing but set of all f in script L to AB such that integral A to B mod f square d lambda is 0. So this is nothing but set of all L to AB such that this is f equal to 0 almost everywhere with respect to the Lebesgue measure lambda. So n consists of almost everywhere 0 functions. Okay, now we define L2 of AB as script L2 of AB quotient with n, and the inner product on L to AB can be defined in the earlier method, using the earlier method. So that means if you look at, so this consists of functions of equivalence classes where f is coming from script L to AB. So here f is related to g if and only if f equal to g almost everywhere with respect to the Lebesgue measure, or f minus g equal to 0 almost everywhere with respect to lambda. So L2 of AB is nothing but equivalence classes of functions, but when we take integration of two equivalent functions in the same equivalence class, the integral is same. So for that reason we consider the equivalence classes to be functions only all the time. So that is a convention. Okay, this is one of the important examples that we'll be using again and again throughout the course. So this is the way we can get an inner product from a semi-inner product. Now let us look at one more important question that we asked in the beginning. Suppose we are given with a question 2 So we are given with a nonlinear space. Let X be a nonlinear space. Now can we find an inner product on X which induces the given norm? Find an inner product on X which induces the given norm. Okay, so before addressing this question, let us look at some important property. One important property which induced norm satisfy. So let us look at an inner product space. And norm is the induced norm. That means norm of X is defined as inner product of X with itself and the square root of this. Now, or we can say that norm X square equal to inner product of X with itself. Let us consider, let us take X and Y are from X. Then if you look at norm of X plus Y square plus norm of X minus Y square, this we can write as inner product of X plus Y with itself plus inner product of X minus Y with itself. If we simplify this one, the mixed terms gets cancelled and we remain with, in the first term you will get norm X square plus norm Y square. Second term also we remain with norm X square plus norm Y square. On the whole you will get, this is 2 times norm X square plus norm Y square. So this law is known as the parallelogram law. This law is an exact generalization of the parallelogram law that we study from Euclidean geometry. Let us look at the parallelogram in the Euclidean space. Take two vectors X and Y. Look at the parallelogram. This is Y, this is X. So this vector is X plus Y and this vector is X minus Y. So this length is norm Y, this length is norm X, this is also norm X, and this is norm Y. This law says that if you take squares of lengths of the sides and take their sum, then that is equals to taking the squares of lengths of the diagonals and taking their sum. In other words, we can say that norm of X square plus norm of Y square, norm of X square plus norm of Y square is nothing but norm of X minus Y square plus norm of x plus y square. Of course, in this case, the norm is nothing but the modulus. Now let us look at a simple example. Let us take x to be R2 and the field is R. Norm of a vector in R2 is given by maxima mod x1 comma mod x2. Now we can say that this norm does not satisfy the parallelogram law. Let us take the vector x as, we can take x to be 1 comma minus 1 and y to be 0 comma 1. Then we can conclude that x plus y is 1 comma 0, x minus y you can actually 1 minus 2. So if you look at norm of x is 1, this equals to norm of y, whereas norm of x plus y, norm of x plus y is nothing but 1, norm of x minus y, this is nothing but 2. So norm x plus y square plus norm x minus y square is nothing but, this is y, while 2 times norm x square plus norm y square, this is 2 times 1 plus 1, that is 4. So this norm does not satisfy the parallelogram law. If the norm induced by the inner product, we know that it satisfies the parallelogram law. But if the norm does not satisfy the parallelogram law, hence we can conclude that this norm cannot be induced by any inner product. So therefore we can say that cannot be induced any inner product on R2. Now we can ask the question, suppose we are given with a norm which satisfies the parallelogram law, can we say that there exists an inner product which induces the norm? In fact, this answer is true. So this is known as von Neumann Jordan theorem. So this is well known as von Neumann Jordan theorem. It says that let X be a nonlinear space then there exists an inner product on X which induces the norm if and only if the norm satisfy the parallelogram law. In this case, we can actually write down the inner product using the norm. So in this case, inner product of X with Y can be given by the polarization identity, that is nothing but 1 by 4 times norm X plus Y square minus norm of X minus Y square plus norm of X plus IY square here multiplied by I minus I times norm X minus IY square. So this is when F is a complex field. In the real case, inner product of X with Y is nothing but 1 by 4 times norm of X plus Y square minus norm of X minus Y square. So when the norm satisfies the parallelogram law, then we can say that there exists an inner product which induces the norm, and the inner product is given by the polarization identity. So this is called polarization identity. This is a very useful identity, and this parallelogram law is also very important, that we will be discussing at a later stage.